further ado, here are the speakers on APT.
Hi. If something goes wrong, it's because of the shot, right? Okay. I'm Sergio dos Santos. I come from Spain, head of security and lab in 11 Paths, which is the Telefónica cybersecurity unit. And
I'm Sheila, and I work as security researcher as well in 11 Paths. I'm 23 years old, and I came from Argentina. Thank you. Well, let's start. In the world of threat intelligence, determining the attacker's geographical location of is one of the most valuable data for attribution techniques. However, in some cases, tracking a malware developer can turn into a pretty difficult thing, and the researchers start getting mad and even feels a little bit frustrated. That's why we are always paying attention to new techniques that might help to track malware developers and reach the potential origin of a malware campaign. In this presentation, we'll focus on Android, first talking about two new techniques that we found to track Android malware developers by getting the time zone of them. The first technique has to do with a bug inside the Android SDK, punctually in the picture. This bug makes a time zone disclosure of the computer where the developers have compiled their malware. And the second technique is related to a calculation of creation times between the certificate of the APK and some files inside it. Throughout our talk, we'll get deep in these two new techniques, and finally, we'll talk about how we can do an accurate from the time zone that we got to a specific country. So let's start talking about the Android bug. When we download the Android SDK, it comes with a tool named APT. We can find this tool inside the SDK folder under Build Tools API version. And if we run APT, we can observe in the first line that this is the Android asset packaging tool. So we can use this program from command line to add some files to an APK, dump the file, see their information, among other things related to APK's management. Due to an APK shares the PK-zip standard, every file inside it has a date and time of last modified. However, when we use APT for adding some files into an APK, we notice something strange in these date and time fields. They are not the real ones. Instead, the right date and time information, we usually saw something like 010180, an hour, and 00. That 3 in the hour field caught our attention because if we change the time zone of the computer to, for example, GMT plus 8, that 3 turned into an 8. And if we change the time zone to GMT plus 4, the hour was 4. So what the hell is happening here? Is this a kind of GMT offset? Well, after we noticed that, we started to analyze the source code of APT. It is published on Google Git, and inside the path of APT, there are several files that compose the source code of this program. So we put our attention in those files related to zipping process. Inside the zip file.c++, there is a method named addCommon that is invoked for every file that will be added to an APK. As we can observe, this method receives as parameter the file name, the size, and some other thing related to the file being stored into an APK. So, analyzing the code of this method, we observe that there is a call to another method named setModWhen, using as parameter the modWhen variable. If we look for this variable, we find that it's a time t type and is initialized to 0. It should be used inside the setModWhen method, so let's check this code. Setmode when is located into the zip entry.c++ file of the source code of AAPT. There we have the method and its parameter. Remember that when is equal to 0. And inside this method, there is another variable of time t type. It's named even. And the value of even is the value of when. So even is equal to 0, 2. But the question here is the even variable used for anything at all? Well, immediately after the lines that we saw before, even is used as parameter for local time function. PTM is a TM structure where local time will save its result. And after that, the result is used for assigning the last modifier field for every file that will be added to an APK. So, at this moment, we have a problem identified. In AAPT, local time function is receiving as parameter the even value, that is 0, when the expected argument for local time function is a real timestamp. So let's analyze it in runtime. Here we are attached to AAPT. We have run the debugger with parameters for adding a file. We put a breakpoint on the subroutine that we were analyzing in the source code. And at this moment, we can observe the even variable with value 0 being passed to local time function as an argument. The result of this, of course, is the one that we were seeing before, so the time zone disclosure of the computer. But what will happen if we pass to local time function the expected argument? That means a real timestamp. Well, now we have altered the value of even, putting a timestamp of Unix epoch. And surprise, the date and time of last modified was the correct one. So let's show you a video demo with all this in action. Let's open. Starting this. Okay, the computer is in GMT+3. We have run the debugger with two parameters for adding two files. We put a breakpoint, and we reach the breakpoint for the first file, but this time we won't fix anything, just we will leave in the even value to 0 as normal execution. But for the second file, we will fix this bug. We'll put a real timestamp, Unix epoch, of course in hexadecimal. We are changing the value of even from 0 to the real timestamp. We continue the process and it will finish. So we can use now APT for extracting the dates of any APK. So now we can see this APK with the first file with this bug making the time zone disclosure and the second file with this bug fixed. Yes, showing the right date and time information. Well, at this moment we are convinced that there is a bug inside AAPT, but why does this end in a time zone disclosure of the computer? Well, local time function makes a calculation to put the correct hour in the hours field. It takes the Unix epoch coming from the parameter, that is UTC0, and makes a sum or subtraction with the time zone of the computer. For example, if the time zone of the computer is GMT plus 3, it makes the Unix epoch plus 3 hours. And if the time zone is GMT minus 3, it makes the subtraction, the Unix epoch minus 3 hours. With that, local time function gets the correct hour in the local computer. But in APT, where we found this bug, local time is making a sum or subtraction over 0. So GMT plus 3 is just 0 plus 3. That's why we will see in the hour fields the 3 number. In the case of GMT minus 3, it's the subtraction 0 minus 3. But this subtraction affects the date too. Now we'll see December 31 of 79 and a 21 in the hour. That 21 is the result of the subtraction 24 minus 3. So those GMT offsets of GMT minus whatever might look a little bit confused. So for that we made an offset table that will be shown you later. And there's a little detail. When we use APT, instead of seeing December 31 of 79, we see an 80 in the year field. That is because of a correction factor in the method that we were analyzing in the source code. There we have an if which says that if the year is less than 80, the year is 80. So it's a little detail, but let us know that we are analyzing it correctly. So here we have the offset table. In the case of GMT plus something, it's very easy because it's the same number. So for example, GMT plus 5 will put a 5 in the hour field. In the case of GMT minus something, we have to do the subtraction. 24 minus the local time of the computer. For example, 24 minus 3 for GMT minus 3. That is 21, and 21 will be the offset in the hours field.
What we have done here is mapping the GMT that we guess it is with the file date in the APK itself. So you can check the file and then get back to the GMT and the local time zone of the one that compiled it.
After all, a good question is, should local time return this? Well, in several documentations, we can see that local time should return a null in this case, instead this information disclosure, because 0 is not a valid argument. So, however, we can see in the IDEA screenshot the return of this function to be sure that is local time the one that is not handling the errors correctly. There in red, we can see the GMT offset 3. In this case, it was GMT plus 3. We have to know that this bug is present on Windows, Linux, and OS X. So Android developers using APT will be leaking their time zone regardless of the platform on they are developing.
Okay, once we know a technique based on a bug in AAPT, let's talk about another technique that has nothing to do with a bug, but with the way attackers or creators of applications usually work. As we have said, APKs are basically zip files. And every zip file has a date inside, a date and hour. They take it from the last modified field in the local system of the user. And it gets permanently inside the zip file. On the other hand, an application, an APK, has to be signed by a certificate. Most of the times, the certificates are created with no CA. They are self-signed, so there's no CA, and you create it just a few minutes before, a few seconds before you compile it, or in other words, you create these possible certificates for signing this APK you're creating. Certificates are in X.509 format. That means that for the creation time field in their own certificate, they take the time from the file system as well. So if you compile it in this date, the certificate will take the date from the file system, but they do it in UTC time, without no time zone at all. So let's think about it. If there's a signature file inside the APK files, that is the last ones to get in the zip file or the APK. It's the last one, and it takes the last modified field from the local system or from the file system. And we have this certificate that if we think or we assume that this certificate is being created basically in the same moment, a few seconds before the compilation, you get the time in UTC, the same time but in UTC. And in the files, they have time zone included. So in these examples, you can see that if you think that the certificate has been created 15 seconds, the certificate has been created 50 seconds before the compilation, because dates are the same, hours are the same, and minutes are basically a few seconds. Here, you can do the math between both dates and times, and you will have a possible GMT or local or time zone. For example, here is GMT -7. Let's have another example. Imagine that this certificate has been created 4 seconds before the compilation. So the last file in the IPK gets the date on the left, and the certificate has the date on the right. You have UTC on one side and the local time with the time zone of the person in the left side. So that means that this person is maybe in GMT +1. So in a nutshell, assuming minutes and seconds are close in time when you create the certificate and you compile the application, and the certificates and the application are created together, we have information enough to deduce the GMT or time zone of the person compiling it. Because just we can do the math between the UTC in the certificate and the time in the file that is last created when you compile it. For example, here it would be 8 hours or whatever. So, and it works. We have created a little Python tool that checks, on one hand, it checks the certificate creation date in UTC time, and on the other hand, it checks the signature file date. If we assume they were created at the same moment, the developed time zone would be UTC +3, because signature file was created 1 second after the certificate. So the result seems quite accurate. We thought this is a fun example because in the email you can check that it's .er, which is Eritrea, and this is UTC +3, but this is basically a coincidence, and as you can check in the certificate, it seems to come from Russia, which is UTC +3 as well. So now we have these 2 techniques to check by a bug in AAPT, and this certificate technique to know the GMT or time zone of the person compiling the applications. Let's do some statistics. We have a 10 million application set or database that we have checked for both techniques. The time zone leakage by AAPT bug, we have 2,000 more or less APKs with this. And the time zone leakage by date times and certificates, we have almost 500,000 of them in our database. As you can check, as you can imagine, many of them will share results. So for example, with UTC +7, we have like 3,000 applications that has both problems, and they leak the same UTC +7. So this confirms more or less these techniques and complement each other. Once we had all this information, what we did is taking 1,000 samples with each leak, 1,000 of UTC +0, 1,000 of UTC +1, with the AAPT time zone disclosure back. Some of them we didn't have enough. For example, UTC -7, we only had 6 of them because this is America Samoa in the middle of the Pacific, and we think there are not too many applications created there. So we checked that against different antiviruses, 1, 2, +3 antiviruses, and check how many malware was there. This is what we got. We got that GMT +4, which is Russia. Russia is usually +3, but a part of Russia is +4. GMT +8, which is China, and GMT -7, which is USA West Coast. GMT plus 11 and GMT minus 8 are not good enough because we didn't have enough samples. We did the same again with the file certificate daytimes disclosure technique. We took 1,000 samples with every time zone, different time zones. We took 1,000 of them and checked against different engines with antiviruses. And this is what we got. We got that GMT plus 5, GMT plus 8, and GMT minus 6 were the ones with more malware in there. If you imagine, why this little difference with the other technique here? Well, we think that this is because of the DST time, daylight saving time. That this technique is relays on the local time of the computer, so it may change. But if you think about it, GMT plus 8, which is China, and do not use DST changes, remains the same. So we can conclude that we should have done this better. We should have taken into account the period of the year where you just change the DST time. Okay? But basically what we can conclude is that Russia, which is GMT plus 4, GMT plus 3 and 5, GMT plus 8, which is China, and Middle USA or West Coast, are the ones creating more malware. With this technique, they're creating disposable certificates as well. You have to take this into account. They're creating disposable certificates. So this makes sense because maybe we think, it's just a theory, that the cloud is too many computers in USA, in the West Coast, and they create certificates in there, disposable, and that's why we have so many malware in there. We did it here the other way around. What we took is all the malware we had with these leakages and checked for the UTC or GMT time zone. And this is what we got. Again, with one technique, the file certificate daytime technique, we got that UTC minus 6 and UTC plus 8 were the ones with more malware. And with the other technique, the AAPK back time zone disclosure, we had basically the same, UTC plus 8 and UTC plus 4. And what is it useful for? What we did as well is check our database. We had 10 million of them, and we had got several sets of 1,000 applications. And we have a rate of 6% of malware in there. And we took a set of 1,000 APK samples with these leakages or disclosures and compare each other. And we conclude that the chances, for example, with the comparing our standard rate, 1,000 applications, which is 6% of malware, and a random set of applications with UTC plus 8 makes it 6 times more likely to be malware than our standard rate in our database. Let's see some examples with real-life malware. For example, this death ring, preloaded in some telephones, had this file certificate dating problem that it was leaking the time zone, and it was Korea, UTC minus 9. And so did UD malware, which had this AAPT time zone disclosure back, and it was Korea as well. This is a malware we found a few years ago. It was a very interesting malware that used, once the mobile was infected, it took some users and password from the database of the attacker, preloaded a user and password, came to the telephone that was infected, registered it with this telephone and email and everything in Google Play, got the token back to the attacker, and with this token they were associated with the telephone, he was able to give 5 stars and download fake applications. Fake users registered to real telephones, voting and downloading fake applications just to get up high in in the Google Play Store. This is called Shuaban. Well, we found it focusing on this bug, GMT for 8, which is China, and some other things like connecting to a PHP command and control, having this get account permissions, and hiding behind wallpapers applications. Focusing on that, we were able to find and define this malware. And we alerted Google Play and they removed it, and it was quite nice to research. That's all malware comes from China. Now, we have, for example, HIDAD, that we took a few samples from them. We checked this malware had both techniques. You could check that with both techniques, that it came from GMT plus 3, which is Russia again. And aside, here you can guess in a way that certificates are always created about 2 or 3 minutes before the compilation, which lead us to think that they were like automated. These possible certificates created in an automated way and coming from Russia.
Okay, with the technique that we were analyzing, probably we'll get the time zone of the Android malware developer. Now we see quickly how we can do an accurate from the time zone that we got to one specific country. Inside an APK, there are some files pretty common. One of them are the RTF documents. Usually they are used for agreements inside Android applications. Related to this kind of file types, we had an inspiration some months ago when WannaCry occurs, because this ransomware shows message in multiple languages using several RTF documents.
There's a funny thing, a trick with Word, Office, and RTF files. When you create an RTF file with Word Office, you get inside the RTF metadata. It's called /deflang. This is your default language in your Word or text editor. So every one of us has a default language in our Word. So it leaks through RTF files. And maybe if you have it's quite possible that your Word file has the final languages is your native languages. So it leaks maybe your native language to RTF files that you create with Word.
Yeah, we made a research for getting information about WannaCry, and among other things, we checked those RTF documents for metadata, and as a result, we found that Korean is the default language configured in the text editor of WannaCry's developer. Well, here we have an example of an Android malware, which among its file there is an RTF document. We have to know that neither Android Studio nor other IDs remove the metadata from the media files added by the developer to an APK. So we can check this kind of media file and get some interesting information. In this case, we found that Arabic is the default language in the author's text editor. There is another trick to accurate the country. Is we can get the strings typed manually by the developer. It may be helpful for knowing the native language of her. We can use apt for extracting a string of an APK, but there's a problem because even if the APK is extremely simple, there will be lots of strings added automatically by the ID just for translation purposes. So in the screenshot we can see thousands of strings. All of them were added by the ID automatically in a very, very simple APK. So we can do a little bit of magic using apt for extracting all the resources, filtering by strings using grid together with regex. A pretty nice command. Analyzing the output of this command, we found a way to differentiate those strings added automatically by the ID from those written by the developer. Basically, we are checking the origin of the strings, removing those coming from resources where strings of translation are. After all, the only thing we have to do is to check what could be the native language of the developer, just seeing the strings typed manually by him.
And we created a tool as well, which is not online yet. But what is it? Here. This is not the best samples in the world, sorry, but you can drag and drop an application and it will try to deduce the possible GMT and check for another techniques to get the country and the languages. The country basically sometimes comes from these techniques we have explained it, or maybe with the certificate itself, or maybe analyzing the strings.xml that we have shown, or even sometimes maybe from the TLD domains, the whatever that the application has inside. So you can deduce with these different techniques, which is the GMT time zone or the language, the native languages of the person. This tool takes all these techniques together, and once you drag and drop whatever APK, you will check different techniques to get in there, even the RTF that we have just talked about. So I hope this tool will be online soon. The other one is already online. This one, for example, says that it comes from Russia and has some domains with TLDs, and the certificate is the standard one for the Boolean, so it's not useful. So, what are the conclusions here? Is that we presented different ways for not just leaking time zone, but as well possibilitating automatic malware creation because of these possible certificates that are created a few seconds or minutes before the compilation is done. Possible better machine learning features in detecting APK malware. Remember that we said some statistics that could be useful once you create a machine learning algorithm. It's useful to have neat features to have a better understanding. So I think this is a pretty good one for machine learning and detecting malware, the ones that are created with these possible certificates or comes from one time zone or another, and a tool for a quick view of all this information around APKs metadata. Feature work, as we said, should take into account the DST, so it's more accurate, these techniques, and maybe have a little more sample, more than 1,000 samples of each disclosure technique or whatever. And this is pretty much all. Thank you. If you have any questions? No questions. That's one. Not too difficult, please. Not with WordPad and this stuff, it doesn't work. Just work with Word, we check because it has the default language defined in there. WordPad, for example, you create an RTF file with WordPad, you don't have a language. Take into account that this language is the one you have defined in your text editor to the syntax correction. So I don't know any other Office package, but with Office Word it happens. Okay, no other question? Thank you. Hope to see you in some other reference.